Hello again. Let's keep talking about some of these theories that are going to help us determine shape and angles. The next one we're going to talk about is hybrid orbital theory, but I kind of wanted you to see how they all went together. So the first thing we learned was atomic orbital theory. Okay? That is your S's, your P's, your D's, and your F's. All right, so your electron configurations. The next one that we learned is valence shell electron pair repulsion. Now, the reason that we really like that one is it predicts the shapes of molecules, okay? It's really nice for that. And of course, the angles. Well, there's one called hybrid orbital theory that shows the electrons in terms of molecular shape, and it uses something called an overlap of an orbital, but it's going to tell us shape, it's going to tell us angles, but it's also going to tell us something about the predictability or the probability of, molecules being formed or atoms binding together. All right. Generically, there's something called the valence bond theory. And so a bond forms when the following are met. Okay, so both conditions must be met. An orbital on one atom, which is one of those atomic orbitals, S, P, D, or F, comes to occupy a portion of the same region of space as an orbital of the other one. So basically, there's overlapping. And the total number of electrons in both orbitals is no more than 2. And let me give you a visual of this. So in order to make a bond, for instance, we would have an S coming close together to another S. If those two came together, they would overlap, and this overlap region is what we would call the bond. And so that is what we would be looking for, which is great. And if we had two P's come together, if they overlapped, we would get something like that, which would be a bond, which is a true overlap. Now, I love that, except when we start talking about the atomic orbitals, okay, so these are the atomics. That looks really fuzzy to me. Why is that looking fuzzy to me? Let's make it a little bit smaller. All right. In order to talk about these, we need to talk about energies as well. And so, for instance, if I take carbon, it has helium plus 2s2, 2p2. So that's the electron configuration. The orbital diagram would look like this. So 2s and 2p, and then we would put our valence electrons in there. Okay, that is what carbon looks like, but that's carbon as the atom. I don't want carbon as the atom. I want to know what is it going to do if something comes along and it can actually bond. And so we're going to use this hybrid orbital theory because right now it looks like, hey, there's a great spot for 2 electrons. Ooh, you could accommodate one more. You could accommodate one more. So right now it looks like there's only 3 places to bond. And then one of those, somebody else has to donate both electrons. Now we know carbon doesn't do that very often, so we're going to use this new theory called hybrid orbital theory to explain the bonding, specifically of any atom, but I just happen to start with carbon. So let's go ahead and clear this. All right, so let's look at carbon's options. So why is that gray? Oh, well, I guess we will live with gray. All right, so carbon has 2s and a 2p. And I will show you 2 ways. I'll show you the visual and the other visual. Yeah, that was really helpful. So what we're going to talk about is a hybrid. And a hybrid is an overlap to form a new location, okay? This new, and they're called hybrid orbitals. So what are our possibilities? We could have an S come in contact with a P. Okay, that was an ugly P. All right, but if you add those two together, those are two atomics, and they would come together to form two hybrids. Oh, wow, I'm drawing very terrible. So two hybrids. So two atomics would make two hybrids. And what is the best arrangement of these two hybrids? Well, of course, 180 degrees. And so that explains family linear. And so hybrids, you have to combine them. So if you're hybridizing, what options do I have? Well, if you have S's and P's, you always have to start low energy and go to high. So the smallest you could do was you could make two P's, or sorry, two SPs and leave over two P's. So SPs, and then those are your leftover atomic orbitals. So here's your hybrid orbitals, and there's your atomics. Or another possibility would be 1, 2, 3, and you'd have one leftover P. And we're so creative. It's called an sp2 because you use the s orbital and two p's. And then last but not least, what if you used all of them? We call those the sp3s, and there are no leftover atomic orbitals. So if you have access, or the atom has access to the s's and the p's, those are the variations. Those are the variations. And we would call the combos hybrid orbitals, and we would call the others, or the ones that weren't used, atomic. And remember, the d electrons are out there eventually. So they can also have d orbitals. You can either use them to hybridize, or they can just sit there and be empty. The only time you have to draw them, though, is if you have used some of them to hybridize. So that is overall what a hybrid orbital is. And we haven't used it yet, but I kind of wanted to show you with my wonderful drawing skills. You know, I'm going to leave this and go back in, and maybe it'll go back to my black writing. All right, so for your hybrid orbitals, nope, it didn't. Here's the ideas that I'm trying to make. If you have an S, and then you have PY, PX, and PZ, so those are your three P's, you can combine just these two together, and it would make two equal hybrids. But what is left over? You would get your PY, and you would also have PZ. This would be called an SP. So you'd have two SP hybridized, but you would still have your PY and your PZ. If you combined three of them together, you would end up with three sp2s that all have the same energy, but you would still have, I'll just call it the PY, you would still have one leftover atomic p orbital. And then if you had four, it would look, oops, I didn't want to be red. You would have four sp3s and no atomics left. So this looks like this. This one looks like this. And this one looks like that. So if you'll notice, VSEPR theory and hybrid orbital theory share a lot in common. And it will also help us predict angles. But we already got that from VSEPR. So 180, 120, and 109.1. That's the basic idea. But one thing that hybrid orbital theory will give us that VSEPR doesn't really talk about is, well, where do double bonds and triple bonds come from? And the double bonds and triple bonds, so multiple bonds, have to have atomic orbitals, and I like to call it interact rather than overlap. And that is going to be another video. So generically, as a review, what is hybrid orbital theory? Hybrid orbital theory is going to take atomic orbitals. They are going to hybridize. That's not how you spell that. Hybridize. They're going to hybridize and they're going to make bonding locations. Anything that is not used is still available as atomic orbitals. This is going to help us explain lone pairs. It's going to help us explain single bonds, double bonds, triple bonds, and it will also tell us about angles. All right, until next time, and we'll talk about it some more. Jolly out.